Hello, geometry friends. Today we are going to continue a discussion that we've been having about simplifying and manipulating radicals. Yesterday we just had radicals that were kind of, out in the wild, and today we're going to talk about what if you need to operate on radicals, like multiply or divide radicals. What do you do then? All right, so in the top here, we've got an opening exercise, simplify the following. You should be able to do each of those on your own. So I am going to actually leave that to you for a second. So I'm going to pause this video, do those three, and then come back. Pause it. Okay, maybe you're back now. What's the square root of 3600? That's going to be 60, and the square root of x to the 500 is going to be x to the 250, because when you square root something with a power, it cuts the power in half. Square root of 25x cubed, I'm going to separate that. 25 and x cubed. 25 becomes 5. X cubed is x squared times x. So this is 5x radical x. And 98 is 49 times 2, which makes this 7 root 2. All right. We've kind of already done the first part of this lesson up in that opening exercise, because it's about what happens if you multiply or divide radicals. Well, I kind of already multiplied radicals right here. When I turn this root 25x cubed into the square root of 25 times the square root of x cubed, I use the multiplication of radicals rule, that if you multiply one square root by another square root, the square root stays and you separate the inside, okay? Or you multiply the insides. Same thing happens for division. If you have the square root of a quotient, you can square root the top and square root the bottom, all right? That's really all it comes down to. So like in A, it says find the square root of 6 times the square root of 3. Well, the square root of 6 times the square root of 3 would be the square root of 18. I just multiply 6 times 3. The radical stays. But now I want to look at that 18 and see if it breaks down and say, okay, 18 is 18 times 1 or 9 times 2. Ooh, 9 is a perfect square. So I'm going to rewrite the square root of 18 as the square root of 9 times the square root of 2. And make that 3 root 2. In B, I have 3 root 8 times 4 root 5. If you have a coefficient and a radicand, the coefficients get multiplied and the radicands get multiplied. The radicand is the thing inside the radical. 3 times 4 is 12. 8 times 5 is 40. And then I want to say, okay, what's the biggest perfect square that goes into 40? 1 times 40. 2 times 20, 4 times 10, 4 is a perfect square, and then 8 times 5. So 4 is the only perfect square that I can pull out of 40, the only factor of 40 that's a perfect square. So I'm going to rewrite square root of 40 as square root 4 times square root 10. The square root of 4 is 2, and so this becomes 24 times the square root of 10. Square root of 2x squared, square root of 6x cubed. Same thing. I see stuff inside the radical, so I'm going to multiply that stuff. 2x squared times 6x cubed becomes 12x to the 5th. Then I'm going to go back to what we did in the previous lesson and say, well, then that means that that's the square root of 12 times the square root of 5. Now I'm going to break 12 and x to the 5th down into their components that are perfect squares and non-perfect squares. 12 is 4 times 3. X to the 5th is x to the 4th times x. So I get 2 root 3 times x squared root x, which is 2x squared times radical 3x. And then just a couple more down here. I feel like switching colors. We started with red. Let's go in rainbow order. Let's go to orange. So radical 5 times 5 radical 4. Well, what is this 5 getting multiplied? Technically, there's an invisible 1 in front of any radical sign that doesn't have an obvious coefficient. So this would be 5 times 1, which is 5. And 5 times 4, which is 20. And then I'd say, oh, okay, so 20 is 4 times 5. Root 4 is 2. So this is 10 radical 5. Now, I don't know if anybody's thinking it, but you may have thought, wait a second, Mrs. Weber, isn't there a better way to do that? And the answer is yeah, I would say a better way to do that. When I look at that, I realize, wait a second, if I don't rush to multiply, I realize that the square root of 4 is a nice number. So I could just change this immediately into root 5 times 5 times 2, which is 10 root 5. And not have to ever multiply the radicands together because this opening radicand was a good one. Either one of those is fine. You get to the same answer. All right. Square root of x times square root of 4x. Okay. I'm going to multiply these radicands. X times 4x is 4x squared. That would be the square root of 4 times the square root of x squared. Square root of 4 is 2. Square root of x squared is x to the first. Now, there's something that I'm realizing right now that I didn't say in this video or the video before it, and that is we are doing all of these things assuming all variables are positive. Okay, so this is where Mrs. Weber does that thing where she gets on her little mathematical soapbox to teach you something. What does that mean, assume all variables are positive? Well, here's what I mean. We've been doing things like the square root of x squared is x, that you divide the exponent by 2. But technically, the square root of x squared isn't just x, it's the absolute value of x. Okay? The reason for that is, what if I did the square root of -3 squared? Well, -3 squared is 9, and the square root of 9 is 3. In other words, by square rooting -3 squared, I got +3. The negative disappeared. So, in the wild of mathematics, the square root of x squared is technically the absolute value of x. But for this class, we are going to assume that the x or any other variable was positive from the get-go. So we've been ignoring these absolute value symbols for this class. In later classes, you'll find out that that is true. Okay, so back to our regularly scheduled program. And let's do some more radicals. All right, 3 plus the square root of 6 squared. Now, you may be tempted to say, oh, wait, Mrs. Weber, can't you just make that 3 squared, which is 9, root 6 squared, which is 6, and that's 9 plus 6 is 15. No, you cannot distribute an exponent to addition or subtraction. It doesn't work that way. Okay, so when you see an exponent outside of something that has addition or subtraction, you cannot distribute it. You have to use what that exponent really means. And in its soul, squaring something means multiplying it by itself. So 3 plus radical 6 squared is 3 plus radical 6 times 3 plus radical 6. And if I want to multiply two binomials, we're going to go to what you did last year, and we're going to do the box method. So 3 plus the square root of 6 times 3 plus the square root of 6, I am going to multiply using that multiplication table we create. 3 times 3 is 9. 3 times radical 6 is just 3 radical 6. This is another 3 radical 6. And root 6 times root 6 is, well, I have 2 radicals. I'm going to multiply their insides. That's going to be the square root of 36. And the square root of 36 is just 6. When you multiply a radical by itself, the square root just disappears. And so then I have 9 plus 3 root 6 plus 3 root 6 plus 6. And if I combine like terms, the 9 and the 6 make 15. 3 root 6 plus 3 root 6. You say, well, I have 3 radical 6s plus 3 more radical 6s for a grand total of 6 radical 6s. Okay. All right, so red, orange, yellow would come next, but that seems silly to write in, so I'm going to go to like a light green here. 6 times the square root of 20 over 2 times the square root of 5. If you have something set up like this, you can think of it a lot like this one, where if I had a coefficient and a radical times a coefficient and a radical, I multiply the coefficients, I multiply the radicals. Same thing for dividing. If I have 16 root 20, and 2 root 5, I can divide the coefficients. 16 divided by 2 is 8. And then divide the radicands. 20 divided by 5 is 4. And the square root of 4 is just 2. So this ends up just being 16. Okay. Same thing over here. I have the square root of 17 over 25. So first I divide 17 by 25, and okay, I'm done. I can't do that. That doesn't simplify. So the other thing you can do is say, well, if I have one big radical, it applies to the top and the bottom. So this is the same thing as the square root of 17 over the square root of 25. Well, the square root of 25 is just 5, and 17 is prime. It doesn't have any perfect square factors other than 1. So this just stays radical 17 over 5. Radical 48 over radical 4. Okay, you may be thinking, hey, Mrs. Vibber, is this one of those things where I can say the square root of 4 is 2 and do that off the bat? You absolutely can. Or you can do this by dividing first. And in this case, I would divide first. And here's why. 48, kind of a big number. Okay, in the scheme of things, I know it's not that big, but given what we usually work with, 48 is kind of a big number, and I would love to divide that 48 by 4 before doing anything else. So I'm going to divide those first. The square root of 48 divided by the square root of 4 is the square root of 12, because 48 divided by 4 is 12. And then 12 is 4 times 3, which makes this 2 root 3. Okay, there's multiplying and dividing radicals. Now, here's the thing. When we divide radicals, sometimes something uncouth happens, and we end up with a radical in the denominator, and we don't like that. Okay, you are never allowed to leave a radical in the denominator. Okay, here goes Mrs. Vibber. Side note, yeah, technically you are. It's really not that big of a deal when you get into other mathematics, but you, as a geometry student, are never allowed to leave a radical in the denominator. Later on you can, but for right now, pretend you can't. So you're never allowed to leave a radical in the denominator this year. So if that happens, we need to do something called rationalize the denominator. Why do we call it that? Because if you remember a little bit of your algebra, numbers like the square root of 17 are irrational numbers, because if I type that into the calculator, I get a non-terminating, non-repeating decimal, basically an ugly looking decimal, and so that's irrational. So rationalizing the denominator means getting the square root to go away, so you get a nice, happy, rational number. All right, how do you do that? Well, you do that by basically multiplying by 1. Let me show you what I mean. There are steps up top, but I'm just going to explain the steps as I do it. 1 over the square root of 2. All right, as a 10th grade or 9th grade or whatever grade geometry student you are right now, I look at that and say, uh-oh, I've got a radical 2 on the bottom. I'm not supposed to leave it that way in the class of geometry. How do I get rid of it? Well, geez, if I want that square root of 2 to be a whole number rather than a radical number, what I can do is say, let's multiply by the square root of 2. Because we found on the front, remember when we did that box method, that root 6 times root 6 is just 6? That would mean root 2 times root 2 is just 2. But I can't just multiply the bottom by root 2. I have to multiply the top also. And remember I said when we try to rationalize a denominator, what we're really doing is multiplying by 1? I am multiplying by 1. Root 2 over itself is 1. So I'm not changing the value of the fraction. I'm just changing the look of the fraction. Much like in middle school, if you had something like 4/8, you change it to a half. Still the same number, it just looks a little bit better. All right, so I am going to multiply by root 2 over root 2. So I'm going to multiply the tops. 1 times radical 2 is radical 2. I'm going to multiply the bottoms. Root 2 times root 2 is just 2. A radical times itself, the radical disappears. And now I can leave this be. I have a radical, but it's on the top, and I'm okay with that. Now, you might be thinking, or maybe you're not, Mrs. Weber, why? Like, why can't I leave it that way? Remember in the other video where I got up on my mathematical soapbox? I really should build one, by the way. But remember when I got up on my mathematical soapbox and I said, when we simplify radicals, why do we do that? And I said yesterday, like, sometimes if I have a number like the square root of 113, I might want to leave it that way instead of trying to simplify it, or, better yet, let's say the square root of 108. I might want to leave it that way instead of simplifying it. Can the square root of 108 simplify? Sure, but maybe I don't want to, because if I look at radical 108, I immediately know that as a decimal, square root of 108 is maybe like 10.4. How do I know that? Because 108 is between 100 and 121, which is between 10 and 11 once I square root it. So the square root of 108 is maybe like 10.4. So sometimes I like to leave it in unsimplified form because I can simplify radicals in my head. When it comes to rationalizing the denominator, if somebody put me on the spot and said, hey, Mrs. Weber, what's 1 divided by the square root of 2 is a decimal? I would say, yeah, I don't know. But if somebody asked me what the square root of 2 over 2 is as a decimal, I would know that the square root of 2 is around like 1.5, and 1.5 divided by 2 is like 0.75-ish, and I can estimate this in my head. So rationalizing the denominator is good for doing things in your noodle if you needed to like estimate how big something was. Okay, climbing down off of my soapbox and showing you how to do these now. 5 over the square root of 7. Same problem we had before. Radical on the bottom. To get rid of it, you multiply the top and the bottom by the radical causing you trouble. So this on top becomes 5 root 7. And on the bottom, root 7 times root 7 is 7. And that is it. 2 root 4 over the square root of 3. Uh-oh, there's a radical 3 on the bottom. But you know what I'm also noticing? I have the square root of 4 on top. So before I even worry about that root 3 on the bottom, I'm going to say that the square root of 4 is really just 2. So this is now 4 over root 3. And now I have a problem, so I'm going to multiply the top and the bottom by the radical causing me trouble. 4 root 3 on top, and root 3 times itself on the bottom is just 3. All right, root 8 over root 5. Don't know what the square root of 8 is as a nice number, so I'm going to leave it. Square root of 5 is causing trouble on the bottom. Multiply by the radical causing trouble. Root 5 times root 5 is 5. Root 8 times root 5, I'm going to multiply the radicands to get 40. And then I'm going to say, wait, I have a big radical on top. Let's simplify that. Root 40, 40 is 4 times 10. And the square root of 4 is 2. So that's going to be 2 root 10 over 5. Square root of 18 twelfths. Well, the first thing I'm going to do is simplify it and say, wait a second, 18 twelfths, so those are both divisible by 6. So this is really the square root of 3 halves. Now, this counts as having a radical on the denominator because the square root of 3 halves is the same as the square root of 3 over the square root of 2. So I do have a radical on the bottom, and that's not okay. So I'm going to multiply by the radical that I'm trying to get rid of and say, all right, root 2 times root 2 is 2. Root 3 times root 2 is root 6. And then I think about 6, and yeah, there's no perfect square factors of 6. So now I walk away. Root 12 over root 3. I've got a root 3 on the bottom, so I could multiply by that. Or before I do, I could simplify and say, wait a second, wasn't there a rule that says if you have 2 radicals, you can divide them first? Yes, there was a rule like that. Root 12 divided by root 3 is the same as the square root of 12 divided by 3, which is 4. And the square root of 4 is 2. How are we doing here? 3 more. Let's do it. 3 root 5 over root 6. Got a radical on the bottom. Let's multiply by it. So on top, 3 root 5 times root 6 becomes 3 radical 30. And root 6 times root 6 is 6. And then I'm going to say, okay, 30. Does that have any perfect square factors? 1 and 30, 2 and 15, 3 and 10, 5 and 6. Nope. Square root of 30 doesn't break down anymore. So I could box this in right now. It's been rationalized, but it simplifies more. I have a regular old coefficient of 3 and a 6 down here. If those two numbers that aren't in radicals are reducible, reduce them. 3/6 is the same as 1/2. So this is really 1 radical 30 over 2, and we don't usually put the ones there. We make them invisible. So that's radical 30 over 2. All right, 15 over the square root of 5. I have a radical on the bottom. Multiply by the radical causing trouble. Square root of 15, 15 times the square root of 5 on top, 5 on the bottom. And then I say, wait, 15 divided by 5, that's 3. So this is 3 root 5. Uno mas, and then we're done. 18 over the square root of 3. Square root of 3 is causing trouble, so let's get rid of it. So then I have 18 root 3 over 3. Wait, 18 thirds? That's 6. 6 root 3. All right, gals and ladies and people and humans and maybe pets who are watching this video as well, what are we going to do next? You're going to practice your homework. So practice those questions on the next page. If you need help, there's that QR code there. You can also just Google multiplying and dividing radicals and see if there's a video that explains this better than I did. So I'm going to end with a terrible joke. What keeps a square from moving? What keeps a square from moving? Square roots. All right, let me get off the stage here. I hope you are having a good day and continue to do so. Bye.